Hello everyone! Unlike last year, I had to record a presentation this year due to a conflicting progress meeting I have in Friedrichshafen. So I got the chance again to extend by 1 year my registration to the PhD to have more time to finish it while working besides. Since I am close to the end, today's presentation will be a summary of the complete PhD. I will go through the motivations, the two main objectives, and the contributions of the thesis. So first, let me remind you the context of the PhD. Space telescopes need to perform many maneuvers per year to observe the deep space. These maneuvers happen between observations and can cover large angles. It is important to perform these maneuvers in the smallest time possible in order to maximize the time observing deep space, which is also called the operational availability. Finally, it is essential to maximize the effective area and the resolution of the telescope, for example by having larger mirrors or multiple scientific instruments on board the spacecraft. In order to fulfill all these needs, the space industry relies on new spacecraft design concepts that enable to observe the same target successively with different onboard instruments by using a common primary mirror. Examples for this are the current James Webb Space Telescope and the future ESA Space Telescopes Ariel and Athena. They use a hexapod to move their primary mirror in all directions and orientations. In addition, these spacecraft have rigid and flexible structural characteristics. So two main industrial technical objectives arise from these concepts: to improve the spacecraft maneuver autonomy and to satisfy fine line of sight pointing. So the first objective of the PhD is the line of sight guidance. Based on the previously shown observation missions, a general guidance problem has been formulated. It consists in performing autonomous repointing maneuvers from one attitude to another under safety-critical attitude constraints. In order to prevent sunlight from entering the instrument's field of view, the line of sight should avoid the red cones on the picture and stay within a certain angular range about the YB axis. The second objective of the PhD is the robust modeling of the spacecraft. Indeed, the mass of the mirror, in blue, on the picture, can reach up to 20% of the total spacecraft mass, which induces multi-body and multi-actuator effects on the global inertia and thus on the global spacecraft attitude. This means that the spacecraft cannot be considered as a single body anymore, and treating it so in the control design would lead to discrepancies when simulating it with real effects. In addition, the mechanisms in green on the picture have flexible modes, and they could interact with the solar array flexible modes, for example. So this represents a challenge to the attitude control system, and this is why we need a control model that accounts for all these effects, including flexible modes and parametric uncertainties. So here, the animation just showed that indeed for performing a spacecraft maneuver, we will have to move both the mirror and the spacecraft at the same time. So for the first objective, a state of practice is to divide the multi-axis maneuver into single-axis maneuvers. A first rotation around the YB axis cancels the initial elevation angle by bringing the spacecraft into the azimuth plane. Then a second rotation is performed within this plane. Finally, a third rotation around the YB axis leads the spacecraft line of sight to the new elevation angle at the final wanted line of sight direction. This solution satisfies the attitude constraints, but is very time-consuming since 3 consecutive submaneuvers are performed for each slew maneuver. Since there is no rotation allowed around the ZB axis, the problem can actually be simplified, and I will now show you how we derived a novel solution for this guidance problem. So actually, the permissible zone, which is the complementary of this red zone, can be defined in terms of Euler angles, only using the xb and yb axis. This zone is convex, which ensures that there exists a solution when starting and finishing maneuvers from angles within this zone. Once we have this angular domain, we can find the optimal solution. We can transform this angular domain that we just computed into the momentum domain by using the spacecraft moment of inertia. This will enable us to find the optimal guidance solution using the real angular momentum and torque capacity of the spacecraft. To do so, the ratio from each envelope was introduced. Depending on the needed rotational capacity, momentum and torque capacity for the slew maneuver to perform, this ratio vary. So the ratio, this one is always the same because it depends only on the reaction wheel configuration and characteristics of the spacecraft. However, the ratio from the rotational capacity to the angular momentum and the ratio from this one to the torque vary because they depend on the rotation, so the angle to cover. From this ratio, we can compute the minimum actuation time for the maneuver, and final checks on the available momentum enable to compute the final maneuver time for each maneuver. This solution was implemented and verified in a mission simulator and enabled to increase the availability of the spacecraft, which represents a reduction of more than 20% of the operational time. The results were presented in a conference and published in the Acta Astronautica journal in 2023. So let's now focus on the second objective. For this objective, the main focus was on the hexapod. The low inertia of the hexapod actuators induce a flexibility between the rigid body and the mirror, called platform here. At the multi-body level, these flexible modes can interact with the ones from the solar arrays, or the actuator's motors can excite these interacting flexible modes. Usually in control, we're interested in linear models that relate forces and torques to linear and angular displacements. For common flexible appendages like solar arrays or antennas, explicit state space models are usually derived directly from the modal parameters. But here, hexapod mechanisms contain closed-loop kinematic chains between their base and their moving platform. This adds algebraic constraints to the system of equations. And these mechanisms are ruled by differential algebraic equations, making them highly nonlinear. So the development of a linear model is not straightforward. This is why an analytical characterization is needed here, and this is the first time that this was done for a space control application. So to obtain this K matrix, the starting point is the result of a modal analysis of one hexapod leg performed by the structure department at Airbus. From this modal analysis, the most relevant mode, the axial mode, is kept. Since it is expressed in the local leg frame of the hexapod, it is then expressed in the global platform frame and at the center of the platform. This is done for each leg. The same process is repeated, and once done, all leg stiffness Ki are 6x6 matrices that can be summed, and the sum is the wanted global stiffness, which is again a 6x6 matrix. The main aspect here is that everything is parameterized, and we can resolve and have an analytical solution to the problem. This is a linear combination of sine waves with amplitude and frequencies known. Once we have the solution, we could verify it to check the model consistency and validate it to check the model physicality. Now that a linear model for the flexible hexapod mechanism was derived, the parametric uncertain multibody and multi-actuator model that was derived with the rigid hexapod mechanism can be extended to the flexible ones. So you can find more details of this verification and validation in the publication, since this was published in a conference. So I also added here all the disseminations and presentations that were done during the PhD. And finally, I really need and want to give the final push to be able to submit the PhD as quick as possible. So the draft manuscript that is already partially cleaned up will be the main focus on this month. So thank you all. And if you have questions, please don't hesitate to contact me by email.